Hi, today we're going to do two things. The first thing we're going to do is just plug some numbers into that stability example with the forward Euler, just to get a little bit more of a feel how it works and the conditions for stability. And then the other thing we're then going to move on to oscillation case. So you may remember that I've said that stability analysis only has meaning for particular true solutions. So if you pick your true solutions carefully, then you can span a big range of conditions for your numerical method. So the one we looked at initially was the exponentially decaying. Today we're going to look at the oscillation case, and I'm going to sort of set up how you change the solution for oscillation. Okay, over to the board. To carry on now, we had this forward Euler result from last time. So forward Euler for exponential decay. And the second bit is important and sometimes overlooked. We've got the forward Euler scheme, but we've got a certain scenario or right hand side of the ODE that we're looking at, and we need to evaluate the stability for those different cases often. So when we have, so that's x equals x star. Let's improve the presentation there. X equals x naught, x star equals x naught e to the minus lambda t, and we found that we had this thing called A, which is called the amplification factor, which is 1 minus lambda down to t. Amplification factor. And I emphasized last time, and I emphasize it again right now by putting a big box around it, that this is kind of key to the stability analysis for a certain situation. So we looked at different categories last time of lambda delta t, particularly when lambda delta t is less than 1, A is less than 1, then you get a stable scheme. But what I want to do now is just to plug some numbers in. And just to give you another angle on this result, so let's just plug some numbers in. So if we just say let lambda equal 100, delta t equals 0.1. This should be unstable. Because lambda delta t is 10, so it's clearly greater than 2. So it's in that category of instability where the solution oscillates and just grows with time. But let's just naively plug the numbers in and see what happens. So we would have x dot, and we use that instead of dx by dt this time, equals minus lambda x equals minus 100 x. So the true solution then, given that we're going to set x as first value to 1 just for convenience, will be that x star is e to the minus 100 t. Okay, so that's the true solution. It's still exponentially decaying as before, but this time we just plug the number in. So let's do by hand. Now, most of the time I just suggest just coding up in MATLAB and doing it yourself, but sometimes you can do certain examples, simpler examples, just with pen and paper. If you are intimidated by the programming side of this and you want to get your confidence back a bit, this is quite a handy exercise. But I wouldn't advise doing it all the time. It's far easier and less labor intensive to use your MATLAB code and to learn how to do the MATLAB or the programming language. Anyway, let's just solve by hand. So we know that xm plus 1 equals 1 minus lambda delta t xn, yeah? That's the amplification factor. And of course now lambda delta t is 10, so that's simply 1 minus 100 times 0.1 times xn, which is minus 9 times xn. So each time solution is multiplying through by minus 9, that's a alarm bells off and confirming that it's probably going to be unstable. But let's just do that. Let's do the first step. Let's just consider n is 0. And we know that x0 is 1. That means that x1, n plus 1, equals minus 9 times x0, which is minus 9 times 1, which is minus 9. And if we were to iterate another 9 times, this is where your coding comes in, rather than just using it by calculating, or just multiply by minus 9 as you calculate it 10 times if you want to do that. We then get x10. So after 10 iterations, we have x10 is 3.5 times 10 to the 9. So the numerical solution is huge, but the true solution is much smaller. Let's just write that down again. So x of 10 equals 3.5 times 10 to the 9. But x star is obviously, we just plug in t equals 1. Yeah, so this is after 10 steps, and remember each step is 0.1. The delta t is 0.1, remember, let's write that there. So after 10 steps you're going to t equals 1 in the true solution, so you just plug in t as 1 into that true solution, you get e to the minus 100. So that's a very small number versus a very big number, you know, and instability. And the problem comes back to the choice of, and the problem is the delta t, which is 0.1, it might seem small, is too large for the problem. And we need that lambda delta t is less than 1 for stability. We know that lambda is 100, so that means that lambda delta t must be less than 0.01. Yeah? So we could have actually predicted from our stability analysis what the time step was before. And this is a little microcosm of what can go wrong with numerical methods if you don't do any analysis or any sort of pre-meditation of how things work. If we just ran it blindly with the time step we wanted, it won't work. And the temptation actually, and you've probably been there with code that hasn't worked, is just to go around this horrible vicious cycle where you just change the numbers and rerun, it still doesn't work, change the numbers. It becomes almost like a colleague of mine referred to this as a headless chicken problem. I don't really know, we've all been a headless chicken at one stage in our career. When we just trying mindlessly to get it working, rather than just standing back from the problem and realising, hey, look, the time step is too large in this case. We've got to use a smaller time step. So again, this may be, you may have seen a similar sort of example like this before. There's a lot of principles in here that I want to emphasise and for you to sort of not forget about. Okay, so make the time step. So that is for the exponentially decaying case. But of course there's other solutions, other sort of right-hand sides to ODEs that could be valid. And we have to redo the stability analysis for those in those cases. But what I'm trying to do is pick out sort of fairly, for want of a better word, canonical, typical scenarios. So although we're having to redo it for different cases, that you can still draw very sort of partially general conclusions from them. So the decaying case is very useful. There's lots of solutions of ordinary differential equations out there which involve something decaying as you go forward in time. The other sort of very important case for ODEs is oscillation, and if you put the two together, you actually span a large range of real cases, the decay and oscillation cases. So that's the next one we're going to consider, and it's a little bit more involved algebraically. These are your complex numbers, but I want to just introduce that, and then we'll talk about it later, because we're going to use these two different cases, exponential decay and oscillation, for all the sort of numerical methods as we go forward. Okay, so oscillation case. So let's just draw a picture. If we have an ODE, we have sort of decay, exponential decay. And the other sort of case is oscillation. Let's just draw a sine wave. Okay. And these are two very useful cases. In fact, if you look at the books that do much larger range of numerical methods than ours, they will typically expose it to these two scenarios, the decaying case and oscillation. Of course, you can combine them to a decaying oscillation and whatever. But it's important that we realise that these are not sort of just plucked out from the air. These are just very useful separate cases. So how a case where you've got an oscillatory true solution responds to the numerical method. And ideally, a good numerical method should be stable for both these cases, but we'll find that some of our numerical methods might be stable for one and not for the other. Okay, and that's important going forward. So, but the whole approach again is to set up the ODE, discretize, and then ask what is the amplification factor. But before we go forward, I mean, the basic idea, right, is that we have a true solution which for decay was true solution was x star equals x naught e to the minus lambda down to t. Now, if we do a substitution of lambda to I omega in the analysis, we get x star equals, and allow x to be a complex number now, we get x e to the I omega t. And this is the oscillation. But there's a lot behind this that I want to just unpack before we go forward, the reason we can do this substitution. But algebraically, what we're going to do is we're going to take minus lambda and we're going to substitute it for I omega. So I in this case, remember, is a square root of minus 1. Okay, so these are complex numbers. Yes, just to say, sometimes with numerics, make sure you know whether I is a complex, is square root of minus 1, or is an index of x. Sometimes it's used for that as well, and just make sure you know which is which. Okay, if you use I without defining it prior in MATLAB, it automatically assumes it's square root of minus 1, by the way. So how can we use what's the background? So the remainder of this little video, before we go into stability analysis, which will be next time, I just want to do some background into using complex numbers for oscillation. So what are we actually doing? So we now have an ODE we're interested in for oscillation, which is dx by dt is I omega x. So I, we know, is square root of minus 1. Omega is a constant and it's just greater than 0 and it's real. It's a real number. It corresponds to the frequency of the problem. So it's basically omega is 2 pi on tau, where tau is the period of the oscillation. So we have our friend the sine wave. If we get two similar points on the wave, tau is this period here. Okay, so omega is just 2 pi divided by tau. Okay, so it's a measure of the frequency. So the higher the frequency the wave, the higher omega is. Okay, so it's 1 over the tau. So a high frequency wave is very small tau, and high frequency. And if you're a physicist, you're sort of this second nature. But I gather, so with mathematicians, sort of need to be reminded of the context sometimes, because you're doing more pure and all that. You know what it means. So it's just this length of time between peaks. Okay, so that's omega, and then x. So dx by dt is I omega x. So x is now a complex number. So before it was real, now it's complex. And this is where I want to go into the link between the fact that this is a complex number and the fact that we're dealing with oscillation. Because some of the steps and the details can get missed along the way. And you'll use this sort of approach to solving wave problems a lot, especially if you do more applied courses, especially into year 3 and year 4. It's a very common thing, but I just want to sort of set the background. So this has a true solution now. X star, where it's complex, is x naught e to the I omega t, and where your initial conditions now are A plus IB. So A and B are constants. And it turns out, if you remember your Euler's theorem, that actually A and B are constants which give you them, which project differently onto cosine and sine waves, and will give a mixture of cosine and sine as you proceed on with the solution. So if I call this A, so we often, it's very conventional just to write this down in this way, but what we really mean, and some people are who like to be more specific, is really meant by A is simply taking the real component of the left and the right hand side. But you can see why this gets a little bit cumbersome all the time, putting these reals around everything. And you want to so the reals are often dropped for convenience. But I'm going to sort of what I wanted to show is that that this equation here corresponds to so really we would call this a star or whatever, because we've got the reals around it. But this is a different thing. We want to show is that the solution of A, whereas we often write it as e to the I omega t, and that's the most convenient algebraically. Okay. Actually corresponds to a superposition of cosine and sine waves. And I'm conscious I'm running out of time, so what I'm going to do is just state the problem and we'll pick it up next time. So what I want to show when you take the real part of dx by dt, of course the real part I omega x corresponds to a oscillatory solution, and because x is strictly speaking imaginary, I'm going to just call it y, which is real. So y is real. This is what I'm trying to make the link, is you often use ETI omega t blase, but actually there's a real solution corresponding to this, and that is that y is a cos omega t minus b sine so actually this complex solution, when you take the real part x, corresponds to a real solution with cosines and so on. And so it's a little bit involved, this discussion, but I want to, that's the basic point that I wanted to show you, that actually the solution here of dx by dt, when you take the real parts of both sides, corresponds to a cosine solution supervised by a sine solution. So what I want to do next time is just show you that algebraically. Okay. And I'll see you next time. Bye for now.